Euler Theorem. So let's remember first how we found the Fermat theorem. Fermat theorem was saying that for any prime p, we can write that some number a at power p minus 1 is going to be equal to 1 mod p. As long as p is prime, remember, and a had to be different from p and 0. So a greatest common divisor between a and p had to be equal to 1. Those were the conditions for the Fermat theorem. And we have proven that it works for p prime. And now the question that stands out: what happened if p is not prime? That's Fermat. And Euler brought the generalization to the case where p is not prime. What is, we work modulo some number n that is not prime. And we are going to try to make the same steps of the proofs that we did for Fermat. So how did we prove Fermat theorem? Remember, this is one of the questions that can come in the exam. I don't know how you would ask that into an online exam. I used to ask. I'll see if I can ask a theoretical question like the proof of Fermat theorem in the online exam. If I can, I'll ask. So it's one of those proofs that I want you to know because we'll use it again and again. So it's important for you to know it. So the way we did, we started with listing the numbers, okay, that we can have the reminders with respect to n. Now, so we have n that is not prime, n composite. So it is a possible number are 0, 1, 2, and so on, all the way to, what is the last one? N minus 1. And now let's try to generalize. So we'll take again a number a, and we'll multiply with a. Each of them, you remember that's what we did to prove Fermat theorem. We multiply a with all of them. Probably I should write the last one a little bit higher. I'm going to say a times a minus 1. And the result a times 0 and will be equal to 0. I'm going to call it B0 as we did with Fermat theorem. But the only difference from the proof of Fermat theorem is that now I'm going to say mod n. Okay, a times 1, we'll call it again B1. That's exactly what I wrote if you look back online in the proof of Fermat theorem. A times 2, we said that that's B2. That's how we denote it. Mod n. Then we had somewhere a times I equals bi mod n. A times j equals bj mod n. And what can, and so on, also wait, the last one will equal with bn minus 1. What can we know about all b0 to bn? We know that a times 0 is equal to 0, b0 is 0. We want to retrace a step of Fermat theorem. In Fermat theorem, we had the property that the values on the right, b0 times b1 times b2 times bn, they were the same as the values 0 on the left, like 1, 2, 3, 4, 5, n. So 0, obviously, if we are going to multiply on columns, as we did for Fermat theorem, I'm going to just go a moment to Fermat theorem such that you see what we did there, in case you guys forgot. I said here was Fermat theorem. Let's arrive. Sorry, yes, a moment ago. Here was it, right? Do you remember this slide? So we wrote in the proof of Fermat theorem that A times 1 equals B1, A times 2 equals B2, 0 was discarded, mod a prime. We multiplied on columns, and we got here that the product of all this was A at power P minus 1, because we had P minus 1 numbers from 1 to P minus 1. And we had the argument that these numbers on the right, they were all distinct. And the proof that they were distinct was based on the fact that since A was relatively prime with P here, then A times B congruent to A times C, only if B congruent to C. So two of these could be equal, only if the numbers are equal. So since we have distinct numbers here, 1 to P minus 1, all these have to be distinct. And since the only distinct numbers as numbers from 1 to P minus 1 are the same in modulus, it means that this set is exactly the same as this set. So this and this cancel, and you remain with A at power P minus 1 congruent to 1. You remember that? Any question about that? Is it still fresh in memory? So now let's see how we go about generalizing this for a number that is not a prime P. So when we go about generalizing it for a number that's not a prime P, and that's where we are now, we have n. And again, we can have the same, we are going to have the same relation that we saw before, the same logic, only if, okay, we have to get rid of A0, B0, and we'll have to have only distinct numbers on the right. So we'll have to write I congruent with AJ if and only if I congruent with J. Otherwise, saying we should be able to multiply with inverse of A mod n. Is it possible to multiply with inverse of A mod n? Always? When can you multiply with the inverse of A? Only when the inverse of A exists. When does the inverse of A exist? If it's coprime. If it's relatively prime with greatest common divisor between A and n equals 1. Then we have an inverse. Then the numbers are different. So we have to request this, that A is relatively prime, just as for Fermat theorem. A had to be, but there it was not very restrictive because P was prime. So any number between 1 and P was relatively prime. Here, since n is not prime, there can be that are not relatively prime. So if 2 is not relatively prime J, you have to cut all the columns where these numbers are not relatively prime with n. So two numbers, Bi and Bj, are congruent only if Ai congruent with Aj, which happens because we have an inverse, given our requirement that a greatest common divisor of A and n to be 1. We have an inverse, so it means they are equal only if I equals J. So since here all the I's and J's are distinct on this column, it means we are going to remain only with distinct numbers here. And since you remain only with distinct number here, there's one more thing to notice. The numbers that remain here, 1, 2 to n minus 1, that are not relatively prime to n, how many such numbers exist that are not relatively prime to n? For a big bonus. So how many numbers exist, numbers k, such that greatest common divisor of k and n equals 1? How many? The cardinality of the set, you could denote it also as a cardinality of the set. K, so what's the cardinality of k? Is the property the greatest common divisor of k and n equals 1, and 0 between k between 0 and n. So how's the cardinality of this set? That's a very important question. You should know it very well. If you guys were around last lecture, you should know this. Nobody remembers from any element in the set of residues of n. And the answer is Euler totient of n. Now we had a whole course just about that. Euler totient of n. That's the answer. So the number of numbers here is Euler totient of n. That was the answer. So if we cut all the numbers that were not relatively prime with n, we remain with Euler totient of n numbers. So when you are going to multiply on column, you are going to have here a times a times a. How many times that remain? A at power Euler totient of n numbers. That's how many numbers remain. Times probably product of what all the numbers I, where greatest common divisor of I and n is 1. The product has a big pi of all numbers I that are relatively prime to n. Okay, between 0 and n, obviously. And what do we have on the right? On the right, we have b1, b2, bn. What's the product of all these numbers? So I would say the product again of bi, okay, again I between 0 and n, where greatest common divisor of I and n is 1 again. So how much is this? How much is this product of all bi's? The product of all these bi's for the rows that are relatively prime to n is the same again as the product of i's, because these are the same numbers permuted, because they are all distinct, and the number of numbers you have to have here, they also have to be all relatively prime to n, because when you multiply a, which is relatively prime to n, with an I that is relatively prime to n, you're going to get a b that is relatively prime to n, right? You multiply two numbers that are relatively prime, you cannot get one that it's a multiple of common factor. Since it's also they are also all relatively prime, and since there are only Euler totient numbers relatively prime, you cannot have others. You cannot invent new relatively prime numbers, because we know from the proof from last lecture that only Euler totient exists. So they must be the same as that one, as those ones. So they are equal. And equal to what, by the way? Are they equal to 0? If they are equal to 0, we didn't gain anything. What could this product be equal to? Can it be 0? Which of these bi's are equal to a times I? No, it cannot be 0, but it's not 1 either. It has to be what? It has to be, yes, Abdurrahman, it has to be -1. From Wilson's theorem. The same as Wilson's theorem, right? So we are going to have numbers and their inverses. And each number there has inverses in all these sets bi except for 1 and -1. Okay? So since all numbers have inverses except for 1 and -1, it means the product of all of them except for 1 and -1 is 1. And when you multiply also with -1, you get -1. So this will be -1. This will also be -1. -1 you can multiply with -1 in both sides, and you remain that this one will be equal to 1. And that's Euler theorem. So it's a generalization of Fermat theorem that states what I just mentioned, namely with Fermat theorem, with Euler theorem, we have A at power Euler tangent of n will be equal to 1 mod n, but only with the condition that we have just seen. And the condition that we have just seen was here, namely A had to be relatively prime to n. That's the only requirement when for any A where greatest common divisor of A and n was equal to 1. Okay, that was the only requirement. So this is a generalization of Fermat theorem that was proven by Euler and is called Euler Theorem, and the exponent here is called Euler tangent. Okay, everything links together, right? And this is a proof that we have just seen, but written for just the case of numbers ended up product of two primes, P and Q, which is a case that we'll discuss frequently from now on. So if it's a product of two numbers, P and Q, okay, then the numbers that are not relatively prime to n will be P, or the products of the multiples of P or the multiples of Q's. So we remain again with A at power Euler tangent of n. And exactly the proof that we have seen on the last slides. In particular, we have this product equal with this product from Wilson's theorem. They're both equal to -1. Cut them. And we remain with A at Euler tangent equals 1, which is known as the Euler theorem. Let's see a couple of examples of the Euler theorem. Okay, so if we are going to try to go over these examples, we are going to say something like this. Let n be the product of two numbers. 10 is a simple product of two numbers, right? 2 times 5. So let's take A be equal to 3. So Euler theorem is telling us that A at Euler tangent of n equals 1 mod n. Right, so Euler tangent of 10 equals how much? 4. Very good. Let's see. Right? Yes, because it's equal to Euler tangent of 2 times 5, which is equal to Euler tangent of 2 times Euler tangent of 5, which is equal, we have seen the rules last time from the Euler tangent, that these are the rules you should remember. For a prime P, Euler tangent is P minus 1. For a prime P at power A, it's P at power A minus 1 times P minus 1. And for any other product of numbers, it's going to be the product of the corresponding decomposition. So if you have a number of this type, P at power some exponent, Euler tangent of it will be the product of P at exponent minus 1 times Pi minus 1. So we just applied this one, and you have a ton of this on your exam, your final exam. So we are going to have to say that Euler tangent of 10, Euler tangent of 2 times 5, each of them is it's a prime. So you can directly generalize, apply the generalization and say Euler tangent of 2 is 2 minus 1. Euler tangent of 5 is 5 minus 1. So 2 minus 1 is 1 times 4 equals 4, as 3 has told us. So 3 at power, now you have A at power Euler tangent equals 1. Euler tangent is 4, so 3 at power 4 will be equal to 1 mod 10. So now if somebody asks you, what is the last digit of raising 3 at power 20 mod 10? What is the last digit? If I say the last digit, I don't even have to say mod 10. So if somebody asks you, what is the last digit of 3 at power 2020? you raise 3 at power 20 as a last digit, what will it be? 1 outside, yes, Abdullah. It's 1. Yeah, because you can write it as 3 at power 10, everything at power 202. And now 3 at power, 3 at power not 10, 3 at power 4, because you write 2010 as 4 times 505. Right, so it's equal to 1 at power 4, 505, right? Because for it, so it's going to be equal to 1. So it means that mod 10 is 1, so the last digit will be a 1. Right, what about 3 at power 2021? What's the last digit? Assuming you compute 3 times 3 times 3, what will be the last digit? Good, Mohammed. It's 3. Right? Yeah, because it's equal with 3 at power 2020 times plus 1. So it's going to be 3 at power 2020 times 3 at power 1. And we have seen before that ends in 1. And this is going to be ending in 3. That will be congruent to 3 mod 10. Yes? Very good. What about 3 at power 1023? Equals to how much? What's the last digit? The last digit will be 7. Very good, Samantha. Yeah, it's 7, right? Because it comes from 27, right? That's, you write it as 3 at power 1020, which is a multiple of 4, plus 3. So 3 at power 1020, it's 4 times 2, 22, it's 525, plus 3. This all is 1, so remains 3 at power 3, which is 27, so ends in 7, mod 10. Mod 10 is telling you the last digit. Okay? You could have noticed that if you take 3 at power 0, ends in 1. 3 at power 1 is 3. 3 at power 2, it's 9. 3 at power 3 is 9 times 3 is 27. So something that ends in 7. 3 at power 4, say 3 times 7 is 21. So the last digit is 1, and you repeat. So each 4, you repeat. So the only possible terminations are 1, 3, 9, 7. This is why the Euler tangent of here was 10 is 4. Because the last digits are more 10, you only have 4 values that can be repeated. Okay? What if I would ask you to compute the last digit of 2 at power 1023 mod 10? So the last digit, let's not even say mod 10, because you know that when I'm saying the last digit, it means it's the result mod 10. So this is equal to how much? Eight. That's true. How much is 2 at power 1020? Two at power 1024. Very good, very good. So what do you notice? At power 1024 is 2 at power 1023 plus 1, which is ends in 8 times 1 more 2, so it ends in 6. Right, so I think Hussein was the one that said 6 the first time, because that's the right. Result. So the last digits is 6. Okay, I don't know exactly if so we have a 1 or not before, but we arrive at 6. So why did you guys say that here you'd arrive at 1? Because it's also a multiple of 4. So this is a multiple of 4. This is also a multiple of 4, and you guys were saying that it ends in 1. Why? Because right, mod 10. You guys were thinking that 4 is Euler Theorem, right? So something at the power multiple of Euler Theorem would be 1. And why is not 1? So this is not equal to 1. Not equal to 1. Why not equal to 1? It's equal to 0, to 6, not 1. So why? Because greatest common divisor between 2 and 10 different from 1. So if you see a condition of Euler Theorem, we said that it only works if the greatest common divisor between it was here, between a and n is 1. And now I talked about 2, and this 2 is not relatively prime to 10. So you cannot say that 2 at power multiple of 4 is equal to 1. You know, Euler Theorem doesn't apply. Euler Theorem only applies if the base is relatively prime to n. So let's take another case where it applies. How much is 5 at power 2021 mod 15? So what you can know is that we know the last digit is 5, but we were computing mod 15. So it cannot apply because, again, 5 is not relatively prime to 15, right? You cannot use either theorem either, okay? So again, we cannot say that, you cannot decompose it. You cannot use Euler theorem. You can use Euler theorem for 3 at power 2021 mod 15. No, this is also you cannot use because it's also not. So, but you can use 2 at power 2021 mod 15. That's something you can compute now because 15 is not odd. So how much is this one? It's equal to, for a bonus, who tells me the final result for this? Need help? Nobody wants to catch it? I'm going to say that this is equal with 2 at power. The Euler tangent of 15 first to compute is Euler tangent of 3 times Euler tangent of 5 equals 3 minus 1, which is 2 times 5 minus 1, which is 4, equals 8. So we look at the power of 8 that's just before 2021, which is 2016. This is the smallest power of plus 5. So this is going to be 2 at power 2016 times 2 at power 5. Now this one we know it's equal to 1 based on Euler theorem, right? So it remains 2 at power 5, which is 32. Okay, so 32 mod 15, it's 30 plus 2, it's 2. Okay, so the result is 2. Okay. So you'll have such fun in your computations, right? So here are some more examples. That's about Euler's theorem. You have quite. Do you want more? One more example, or it's clear? Can I go further? One more example. So how much is, let's say, mod? Let's take again 12. How much is 5 at power 20? What 2018? The first step is to compute what? Euler tangent of 12. How much is Euler tangent of 12? Is it frozen? Hello? Are you guys following? Hello?
We are hearing you.
Okay, thank you. Okay, so Euler tangent of 12 equals Euler tangent of decomposing prime factors. You remember this is a formula that we have just seen on the top, right? You decompose in prime factors as here, and then you use a formula for prime factors. So you just write Euler tangent of 12 is Euler tangent of 2 to the power 2 times 3. Decompose it as Euler tangent of 2 to the power 2 times Euler tangent of 3, which is equal to our tangent of 2 to the power 2 is 2 to the power 2 minus 1 times 2 minus 1. Euler tangent of 3 is 3 minus 1, which is equal to 2 at power 1 times 1 times 2, which is equal to 4. Okay, so Euler tangent is 4. So again, Euler's theorem says that 5 at power 4, that any number a, including 5 at power 4, will be congruent with 1 mod 12. So you say 5 at power 2018. Now, can you go further? You know that at power 4 it's 1. You have to decompose this. function of 4. So this is going to be equal to, so you write 2018 divided by 4 if that's what you prefer, or for you like the other notations, I think, in front. So divided by 4, and you're going to say that this is going to be equal with 5 times 4, it's 20, right? Then 0, then 8 divided by 4, it's 4, and you say it's 16, and 8 minus 16 is 2. So it's going to be 4 times 500. 4 plus 2. Right, so that's the result of the division here. Okay, so this is going to be equal is 5 at power 4, every single power 504, times 5 at power 2, which is equal to 1, from Euler Theorem at power 504, which is 1, times 5 at power 2, which is just 5 at power 2, which is 25, which more 12 is 25, is 12 times 2 plus 1, so congruent with 1. So the result is 1. Is it clear? Want another example? This is very important. We are going to see this very many times, so it's important for you to know. Let me know if it's not clear. Not clear? Not getting anything on the chat side. My chat is.
Everybody's asking for another example.
Okay, it's just that my chat was not scrolling, so I was not seeing it. Apologize. So let's go mod 60 then. Mod 60. And I'm going to compute 7 at power 2020 mod 60. Okay, this, how much is this? So no, it's mod 60. 60 is not a prime. Yeah, thank you, Samantha. So to check that it's 1, you compute first Euler tangent of 60, which is equal to Euler tangent of, very good, it's 2 square times 3 times 5, which is Euler tangent of 2 square times Euler tangent of 3 times Euler tangent of 5. Very good, which is equal to 2 times 2 minus 1 times 2 times 4. 16. Very good, Bashar. Okay. Okay, so 16. So then 7 at power 2020. You write it as what? You write it as? You write 1 multiples of 16. Okay. So multiples of 16. Say it's yeah, 2000 So we are going to divide 2020 divided by 16 to get a 1. 16 remains 4. Then 42, you get here 2. 32, you remain with 10. 0, 16 divided by 0. 100 divided by 16. Sorry, it's going to be equal with 7, 6. 5, 6 times 6, 36, 6, 3, 9. Remainder 4. So it's going to be 16 times 126 plus 4. Okay, so it means she got it right. It's going to be 7 at power 16 at power 126 times 7 at power 4, which is, this is going to be 1 at power 126. Now 7 at power 4, we are going to compute it with fast exponentiation because it's mod 60. So it's going to be 49 square mod 60. So, okay, so that's, yeah, your colleagues came out with the result, and it's going to be reminder 1. Okay. What I would ask one more example, let's say Euler tangent. How much is Euler tangent of 20 of 100? Okay, so it's Euler tangent of 2 square times 5 square. It's Euler tangent of 2 square times Euler tangent of 5 square. 2 square, it's 2 times 2 minus 1. And 5 square, it's 5 times 5 minus 1, which is 5 times 4. So the total result is 10, 40. Okay. Good. So that's it. Here 49 square mod 60. The fastest way to compute that, rather than computing 49 square, you could have observed that 49 mod 60 is minus 11 square, which is the same as 11 square, which is 121, which is 2 times 60 plus 1. Right. So okay, that's. Do you want more examples, or is that enough?
Wait, Dr. Salagi, I had a quick
Yes.
question from earlier. So if we had it where the base was not relatively prime to the modulo, then we can't use Euler.
You cannot decide.
And so were the answers that we got earlier, those were wrong? So we wouldn't have been able to get an answer at all?
Not with Euler theorem. You cannot apply Euler theorem. You can compute, obviously. You can use fast exponentiation, or you can use a generalization. Let's try to generalize Euler theorem. Okay? Why not? Since we are here, it's a good opportunity. Let's go and generalize. What happens if we don't have a relatively prime number for A? Okay, we are going to get into the next generalization. Why did we have A at power P1 equals A mod P? Because Pi, it was obtained by multiplying with either relation A at power P1 minus 1 equals 1 mod P. We multiply this with A, and we got A at power P1 equals 1, right? Equals A mod P. But rather than multiplying here, we could have looked at another generalization that is stronger. Okay, Fermat theorem was that A at power P1 minus 1 equals 1. And another generalization we have seen was A at power a multiple K of P1 minus 1 equals also 1. Right, because you raise this at power mod P. And we can multiply this with A on both sides, and we got A at power a multiple of P minus 1 plus 1 equals A mod P. And this generalization is stronger. Now, if we take this generalization, then we can look at, so we were working mod the number n equals P1 times P2 times Pk. Let this k over here be equal, this was for P1, let k be equal with P2 minus 1 times P3 minus 1 times Pk minus 1. Then let's write the same relation for, so this was congruent with A, right, from here. This was congruent with A. Let's write the same relation for P2. A was also equal with A at power a multiple times P2 minus 1 plus 1 mod P2. Let this k here be another k. Let's write this as A at power, and this k will be P1 minus 1 times, we keep the P2 minus 1 from there, so we say P3 minus 1, and so on, Pk minus 1, and we had the P2 minus 1 from before. This is also going to be true. And like that, writing continuously, we are going to arrive at this total relation over here, which can be written like that. A is going to be equal with each of these, will be equal with A at power P1 minus 1 times P2 minus 1 times P3 minus 1 times Pk minus 1 mod P1 is equal with A at power P1 minus 1 times P2 minus 1 times P3 minus 1 times Pk minus 1 mod P2 equal all the way to A at power P1 minus 1 times P2 minus 1 times P3 minus 1 times Pk minus 1 mod Pk. Right? And this is true because this is a multiple of P1 minus 1 times something plus 1. Right? Where all here were plus 1 at the end. Right? Plus 1, plus 1. So here was a multiple of P1 minus 1 plus 1. This is a multiple of P2 minus 1 plus 1 mod P2. And this is a multiple of Pk minus 1 plus 1 mod Pk. So they are all true. And what you can notice here is these things are all equal. So you see that A is equal to this mod P1, to this mod P2, and these are the same expression. So then from Chinese remainder theorem, we saw this number over here, A at power P1 minus 1 times P2 minus 1 times Pk minus 1 plus 1 mod each Pi, okay? Mod P1, mod P2, mod P3, they are all equal to A. So what is the Chinese remainder theorem saying? That there exists a unique number. So we have the remainder of A mod P1, we have a remainder of A mod P2, we have the remainder of A mod P3, and they are all equal. all equal with this value. It means that A is going to be equal with this. There's a unique number. That's what the Chinese theorem says, that there's a unique number, and namely this one, A at power P1 minus 1 times P2 minus 1 times Pk minus 1. It's exactly this number mod the product of all Pi. Okay? This is what the Chinese remainder theorem is saying. So otherwise saying this number, and what is this number? P1 minus 1 times P2 minus 1 times P3 minus 1 and so on. It's nothing else but Euler's totient of the product of all the prime numbers. Because that's P1 minus 1, it meant that's Euler totient. So we obtain the RSA's generalization of Euler theorem that says that A at multiple Euler totient of n, right? So the product of Pi was n times, there can be any k around them, so that doesn't disrupt any k, plus 1 will be equal to A mod n. And this is a proof, the final proof of the RSA generalization of Fermat theorem, of Euler theorem. Okay, so it's proving that in fact we can get this relation A of any multiple of Euler totient of n plus 1 equals A mod n. So it's not true that A of just Euler totient plus 1, but even more, A at any multiple of Euler totient plus 1 equals A mod n. Okay, let's see some examples. Okay, so let n be equal to n be equal to 10. And now we can still take a number A that is not relatively prime to 10, like 2. 2 at power 2020, right, is the one we wanted to compute last time. We could not use it, compute it with Euler theorem, but with RSA, we can. Okay, why? We write this as Euler totient of n, here, which is 10, is Euler totient of 2 times Euler totient of 5 is equal to 4, right? So we write this as 2 at power a multiple of 4, 4 times 505. Okay, but what we want to do, we want to write A at power a multiple of Euler totient of n plus 1. So here 1 is missing. So I'm going to reduce a 4. I'm going to say this is 2 at power 4 times 504 plus a 4. So I'm going to write it as 2 at power 4 times 504 plus 1 plus 3. And now this one qualifies. So it's going to be 2 at power 4 times 504 times 2 at power 3, which is going to be equal, this one now from RSA generalization of Euler theorem, this is going to be equal to 2, because A at power k times multiple of Euler totient plus 1 is equal to A. That's the generalization. So this is equal to 2 times 2 at power 3. So this is going to be equal with 2 times 8, which is congruent with 16 mod 10. So it's congruent to 6 mod 10. Okay? So this is a RSA generalization for the Euler theorem. So now that's the question that Axi asked. Okay, and from this one, we can get, from this generalization, we can get RSA theorem exactly how we got the exponentiation cipher from Fermat. Okay, so now in order to encrypt a message, you take the message M and you raise it at the power E, right, mod n. And then in order to decrypt, you take the message and you raise it at a power such that altogether you get a multiple of Euler totient plus 1. And what multiplied with E gets a multiple of Euler totient plus 1? It's the inverse of E mod Euler tangent of n. So the ciphertext at power the inverse of E mod Euler tangent plus n will be equal with C times E times its you get m times at power E. That was a ciphertext at power E inverse mod Euler tangent of n, which is going to be E times E inverse will be a multiple of Euler tangent plus 1, so it will be equal to m based on the algorithm and the decryption works. So this is the RSA encryption algorithm.